I am Yoshikazu Nakai from Japan. The title of my presentation is, Evaluation of Dislocation Density in Bimodal Harmonic Structured Stainless Steel Observed by Diffraction Contrast Tomography using Ultrabright Synchrotron Radiation X-ray, Shoichi Kikuchi, Daiki Shiozawa, Kenji Nonaka, Issei Nakazawa, Keisuke Fujita, Mie Kawabata, and Kei Ameyama are my coworkers. These figures show the schematic relationships between stress and strain for conventional homogeneous alloys. You can see, grain refinement brings high strength, but it leads to decrease in ductility like this. Therefore it is necessary to improve both strength and ductility of materials by the microstructural design. To accomplish this, a new microstructural design, called harmonic structure, was proposed, which consists of the coarse grain structure surrounded by 3D network of fine grain structure like this. Harmonic structure can be fabricated using powder metallurgy. The purpose of this study is to evaluate deformation mechanism of harmonic structured material. To accomplish this, the excess dislocation density in shell and core in harmonic structure in tensile test was measured by diffraction contrast tomography using ultra-bright synchrotron radiation X-ray. The material used in the present study was a stainless steel with a bimodal harmonic structure. Diffraction contrast tomography has been developed by French group at European Synchrotron Radiation Facility named ESRF. For tomography, we usually rotate sample. During a rotation of a sample, grains embedded in a polycrystalline sample produce a bright diffraction spot for a grain that satisfies Bragg's diffraction condition. At the same time, you can see a dark spot behind the sample in the transmitted beam. If the grains have no misorientation, the shapes of diffraction and extinction spots are corresponding to the projection of grain from incident X-ray direction. Usually, we have more than 10 spots for each grain. During the tomographic scan of polycrystalline material, we have lot of such spots from many grains embedded in the sample. By classified these spots into groups belonging to individual grains, three-dimensional shape and location of each grain can be reconstructed. During the rotation of sample, you can find a lot of diffraction spot like these. They consist of Debye rings. This figure shows the enlarged view of this diffraction spot. Usually, every grain has misorientation due to the existence of dislocations. A spot of each rotation angle shows only part of a grain. Diffraction spots appeared over a range of successive images like this. Therefore, summation of contributions belonging to a same grain is required for reconstruction of grain shape. This is the conventional DCT proposed by French group. Our new idea is use the rotation angle spread. It gives information of dislocation density in each diffraction plane. You can calculate misorientation of a grain from the spread of diffraction angle using this equation. Then, you can estimate the excess dislocation density from this equation. We employed two kinds of harmonic structured stainless steel, like these. This is a standard harmonic structured material. Unfortunately, we cannot conduct the diffraction contrast tomography for grains smaller than 10 micrometer. We conducted the diffraction contrast tomography only for core structure of this material. Then, we fabricated special harmonic structured material, like this, where both the grains in core and shell are large enough to conduct the diffraction contrast tomography. These figures are examples of DCT reconstruction of grains in homogeneous and standard harmonic structured materials before tensile test, where colors indicate misorientation of each grain. Most of grains were reconstructed for the homogeneous material, however, only grains in core structure could be reconstructed for harmonic structured material. This slide shows the comparison of the change of the excess dislocation density between standard harmonic structured and homogeneous material in tensile test. The change of excess dislocation density is smaller for core structure in harmonic materials than that for homogeneous material, although plastic deformation was comparable. Then, I think that this result indicates that the deformation of harmonic structured material is localized in shell structure. This slide shows the comparison of the change of dislocation density in core structure and shell structure of specially fabricated harmonic structured material. The change of dislocation density is smaller for core structure than that for shell structure. Then, I think that this result also indicates that the deformation of harmonic structured material is localized in shell structure. Diffraction contrast tomography DCT was successfully conducted at ultrabright synchrotron radiation facility Spring 8 in Japan, and the excess dislocation density could be measured. In tensile test, the excess dislocation density was increased with increasing applied stress. In tensile test, the excess dislocation density of core structure in harmonic material was lower than that of homogeneous material. In tensile test of harmonic structured alloy, the excess dislocation density of shell structure is higher than that of core structure. Thank you for your attention.